All right, so section 13.2 is going to be limits and continuity. I hit the record button and then I forgot to make sure the microphone was closed and like remember what I was doing. All right, so it's just like regular class. So I just kind of want to talk you through this section. It's kind of straightforward and self-explanatory, but you didn't sign up for a correspondence class, so let's talk through it. So we're going to look at the definition of a neighborhood in a plane, understand and use the definition of a limit of a function of two variables, extend the concept of continuity to functions of two variables, and the concept of functions continuity to three variables as well. So we're looking at limits and continuity. Okay, so for functions of a single variable, a neighborhood of C might be defined by an interval, right? A set of all x such that x is between a and b for some c that's an element of this interval a to b. Well, since that's an interval on a real number line, if we go to two variables, we'll kind of use this distance formula as an idea and we create a disk. We'll use the distance formula between 2 points x, y and their generic center x sub 0, y sub 0 in the plane to define a delta neighborhood. So we're a neighborhood. A delta neighborhood will be the set of all points x, y, such that the distance from x and y, or from the point x, y to the center x0, y0, is less than delta. All right, so a neighborhood is going to be in a disk. If it has a strictly less than inequality, it's an open disk. If we have an or equal to here, we'll include the edge, which is also called the boundary. Let's talk a little bit about that. A point x sub 0, y sub 0 in a plane region R is an interior point if there exists a delta neighborhood about that point that lies entirely inside the circle. If every point of R is an interior point, then R is an open region. Okay, so if every point has a neighborhood around it, we're good. It just happens to be an open region. A region must contain its interior points, but it might not have any boundary points. Boundary points is if the neighborhood contains points both inside of and outside of the region R, right? It'll be on a boundary point. So a region that contains some but not all of its boundary points is neither open or closed. A closed region, if we do include the boundary, and whatnot. All right, I think that sentence was right here. Come on, there we go. Yeah. A point is a boundary point if every open disk centered at x0, y0 contains points inside R and outside R. So I didn't point it out here, but that is what I said, so that's reassuring. So the limit of a function of two variables. Let's let f be a function of two variables defined except possibly at x sub 0, y sub 0 on an open disk centered at x sub 0, y sub 0. And let L be a real number. So what is this? Let f be a function defined everywhere except possibly defined everywhere in a neighborhood of this point except maybe at the point. Let L be a real number, then the limit as xy approaches x sub 0, y sub 0 of f of xy equals L. If for each epsilon greater than 0, there corresponds a delta greater than 0 such that we can make the limit as close to f of xy as we want, epsilon, whenever our distance from xy to our central point of our region is less than delta. Right? So we can make these things happen just like we did with limits definitions in Math 1411 here at UTEP. So limit rules, they all kind of just apply here as well. Functions of two variables just the same as they do functions of a single variable. We'll talk about them more. But we could find the indicated limit by using these limits. The limit as xy approaches the point AB of f of xy equals 4. And the limit as xy approaches AB of g of xy equals negative 5. Well, a product rule of limits, the limit of a product is the product of the limits. So it's 4 times negative 5, which is negative 20, which is what we would hope to see as properties of limits go. Let's talk about continuity. A function f of two variables is continuous at a point, x0, y0, If an open region in an open region, my goodness, I can't even read my typing. A function f of two variables is continuous at a point in an open region of R if f of x naught y naught is equal to the limit of f of xy as xy approaches x naught y naught. And that's saying exactly what we had for continuity of functions of a single variable. We have, as xy goes to the point, the limit is equal to the function value. So as long as the limit is equal to the function value, we know we have a continuous function. What happens with continuous functions? We know that if k is a real number and f and g are continuous at a point, then the following functions are also continuous at a point. Scalar multiples, sums and differences, the product, and the quotient, as long as the denominator is not equal to 0 at our point. Composite functions, we know that functions of multiple variables cannot be composed, but as long as we have a function of a single variable, if h is continuous at x naught y naught and g is continuous at h of x naught y naught, then the composite function given by g composed with f of xy, which is not that should be an f, not an h. G, actually this one should be an h. That's the problem. That one should be an h. G composed with h of xy is equal to g of h of xy. It's continuous at this point. If the limit of the composition in the correct order of a single variable and a multivariable function gives us that value, right? If the limit's equal to the function value, it's all good. All right, so let's look at a couple of examples. We're going to find the limit and discuss the continuity of the function. The limit as xy approaches negative 1, 2 of x plus y divided by x minus y. Well, the first thing we're going to do anytime we evaluate a limit is we're going to substitute and see what happens. So we put negative 1 in for x, and we put 2 in for y, and we use our appropriate signs as the function indicates. And we find that this limit is a negative 1/3. We will be able to find a limit, and it will be equal to the function value anytime my denominator is not 0. What makes the denominator 0? If x is equal to y. So we could find the limit, and this function is continuous as long as x is not equal to y. If we look at the limit as xy approaches 0, 1 of arc cosine of x over y divided by 1 plus xy, as we evaluate, we put 0 in for x, 1 in for y. So we're looking at arc cosine of 0 divided by 1 plus 0 times 1. The arc cosine of 0 is pi over 2, and 1 plus 0 is 1, so this is just a pi over 2. Right? So the limit is equal to pi over 2. What do we need for the domain? We know that xy cannot be negative 1. We know that y cannot be equal to 0. And in order to be in the domain of the arc cosine, we know that xy has to be between negative 1 and 1. This particular function will be continuous except for on the boundary points. All right, so not on the boundary points, so we'll go with strict inequalities. It's continuous on its interior, right, on the interior of our region here. All right, so we can extend the earlier definitions of limits and continuity to functions of 3 variables by considering a point x, y, z of an open sphere centered at x naught, y naught, z naught. But it has to be less than delta squared. All right, less than delta squared. So, a sphere makes sense, right? We have an interval in 1 dimension. We have a disk in 2 dimensions. We have a sphere in 3 dimensions. And everything holds, right? Everything that we talked about before. A function f of 3 variables is continuous at a point x naught, y naught, z naught in an open region R if the function value is defined and equal to the limit. That's all it takes, right? If the limit is equal to the function value, we're good to go. The function f is continuous in an open region R if it's continuous at every point inside the region. All right, so let's just find some limits. A lot of definitions, a lot of formality, but when it comes right down to it, when we find limits, we're going to substitute and see what happens. So the limit as xy approaches 1, negative 1 of x squared y over 1 plus xy squared. So we'll put in a 1 for x, a negative 1 for y, simplify, and I get negative 1/2. My grandson's in the background, and he's going to be calling for me, and I'm going to hold tight and do my best to keep recording for you. The limit as xy approaches 0, 0 of x minus y over the square root of x minus the square root of y. When we substitute, it seems like we're going to get 0 over 0, and that's an indeterminate form that tells us we really have to do some more work. But check it out. As xy approaches 0, we can't approach from the negative direction because the domain of the function, right? X has to be non-negative, y is non-negative. Actually, no, it has to be strictly positive, right? So we can't have zeros in the denominator either. And since we can't approach 0, 0 from the negative x or the negative y, this limit is never going to exist at 0, 0. All right. The limit as xyz approaches 0, 0, 0 of xy plus yz squared plus xz squared all over x squared plus y squared plus z squared. Now, I claim that this limit does not exist. Here's why. If we let y and z both be 0, right, y and z all 0, we have a limit that would be equal to 0 over x squared, right? We just 0 in the numerator, just x squared in the denominator, and that's 0. But if z equals 0 and x is equal to y, then we get a limit that's equivalent to x squared over x squared plus x squared. So that's 1 over 2, or 1/2. How can the limit be 0 and 1/2? Right? It can't. The limit does not exist if we can't come to it from every direction and get the same value. All right? Discuss the continuity of the functions f and g. Explain any differences. So f of xy is the function x squared plus 2xy squared plus y squared all over x squared plus y squared, as long as xy is not the origin. If xy is the origin, then f of xy is 0. Now, the only difference between f and g is how we define the point at 0, right? The major hard parts of the function are the same. So let's take a look at this function. We can rearrange, maybe put the x squared plus y squared together and separate. We're used to putting things over a common denominator. Don't forget, we could tear them apart. This x squared plus y squared over x squared plus y squared is going to give us a 1. Then what's left is 2xy squared over x squared plus y squared. And this is a polynomial of degree 3. The highest degree in the denominator is 2. So as we go closer and closer to 0, our numerator is going to overwhelm. We'll get a 0 over a smaller number. So the limit as xy approaches 0, 0 for this function, right, this function will be 1. Here in the definition of f, we've defined f of 0, 0 to equal 0. So f is not continuous. The limit is 1. The function value is 0. Not equal, not continuous. However, here in g, right, they're exactly the same except our definition at the origin. Since the origin is defined to be 1 here and the limit is 1, g is continuous, but f is not. All right? And this bottom one here, discuss the continuity of the function f of xyz equals xy sine of z. No domain restrictions here. Sine is continuous everywhere. This function is going to be continuous everywhere as well. A couple more problems. Last page. Discuss the continuity of the composite f composed with g, where f of t equals 1 over t, and g of xy is x squared plus y squared. Now, we can only take the composition in one order, right, with the multivariable function on the inside. So f of g of xy is f of x squared plus y squared. What is f f is the function 1 over, so f of x squared plus y squared will be 1 over x squared plus y squared. This particular function is continuous everywhere except for where the denominator is 0, and that only occurs when x squared is equal to y squared. That's not true. It's when x squared equals negative y squared, and that's why it's only at 0, 0. All right. For each limit, find each limit for f of xy equal 1 over x plus y. This first one, the limit is delta x approaches 0 of f of x plus delta x comma y minus f of xy all over delta x. We're going to see this as a definition in our next section. So delta x approaches 0. The only thing I see here is that I have some work to do. Let's do f of x plus delta xy minus f of xy over delta x a little larger. So we'll do that over here, and I'm going to substitute. So f of x plus delta x comma y is 1 over x plus delta x plus y minus the original function 1 over x plus y over delta x. Now, get a common denominator. We're going to have a denominator of, we're going to multiply both numerator and denominator by a product of these two denominators, x plus y times x plus delta x plus y. We end up with x plus y on the left minus x plus delta x plus y. Verify this equation if you need to over x plus delta x plus y times x plus y times delta x in the denominator. This is one of those where I might show this step underneath the screen if we were in class. So do the work, hit pause if you need to, and make sure you're good there. Now x minus x, y minus y, all that remains is a negative delta x in the numerator. But don't forget, I have this delta x in the denominator. So the delta x's cancel out, and I can simplify f of x plus delta x comma y minus f of xy delta x with this function. And so I plop it up in here. Negative 1, limit as delta x approaches 0 of negative 1 over x plus delta x plus y, all times x plus y. As delta x goes to 0, I'll end up with x plus y squared in my denominator. Negative 1 in the numerator. So that's my limit. Now, the cool thing is, this function, it doesn't, x, y, they're the same, right? It could be y plus x. There's absolutely nothing we would do different in a treatment for y. So since this function is symmetric and the treatment of x is exactly the same as the treatment of y, our limit as delta y approaches 0 is also going to be negative 1 over x plus y quantity squared. And I'm going to leave that one for you to do the details, just to make sure you're paying attention. All right, that is 13.2, limits and continuity. Thanks for listening. We're probably not going to have a class day to go over this full lecture, but I'll always have time to go over questions when I return.